Hi, my name is Victor Kai. I'm from Allentown, Pennsylvania, and I go to Parkland High School. And my project is on designing a narrowband radar for simultaneous distance and velocity sensing using the low-cost SDR or software-defined radio technology. To reach a 15 centimeter resolution, a traditional radar would require over 1 gigahertz of bandwidth and lots of power, which makes it infeasible for amateur research. And meanwhile, an SDR unit only has around 4 megahertz of bandwidth, which means its theoretical resolution would be over 37 meters. And so that's not good for indoor sensing and short-range sensing. And so that's why you can find many SDR Doppler radars for motion sensing, but no SDR distance sensing radars. And so this project was able to create such an SDR distance sensing radar with a 12 centimeter resolution using only 10 kilohertz of bandwidth, which is 5 magnitudes less bandwidth than that required by a traditional algorithm. And I accomplished this by combining the low power SDR with a lesser known radar algorithm called multiple frequency continuous wave, or MFCW. And that allows me to use the phase difference between multiple frequencies to calculate the distance. And so here's my homemade setup. I have 2 SDR units, 1 per frequency, 2 CAN antennas for the transmit, and 2 panel antennas for receive. The target is mounted on this ruled camera slider for comparison with the actual distance. And then here's my software running in GNU Radio with graphics for demonstration. So here's how I would conduct a test. So first, I would conduct a leakage calibration, which allows me to cancel out any small leakage that goes between the transmit path in the SDR and leaks into the receive path. I do that by first removing this target. And now the receive signal that remains is only the leakage. And so I can cancel that out by introducing another curve here, and then making that the negative image to help flatten out the leakage signal. And so now there is no leakage signal, but when I add the target back, then the only signal that remains is that reflected from the target and none of the leakage. And now I can do a phase calibration, and I do that by first setting the target at 30 centimeters is my zeroing point, and I measure the distance from that point. And then I can adjust the delay in each of these channels so that they're both at a phase of 0. And now the distance shows up as 0. And then to conduct a distance sensing test, I would push back the target in 1 centimeter increments, 1, 2, 3, and so on, and then record those values. So additionally, it's quite simple to apply a Doppler portion to this distance sensing radar as well. I would simply add an FFT block for the frequency shift analysis, and then that taps off of one of the 2 channels that's already existing in the radar. So in conclusion, I was able to create a new phase-based solution that proved that distance sensing is indeed possible on a bandwidth-limited SDR. And this will help to fight the high power and harsh interference typically associated with ultra-wideband radar. Many applications of this project in short-range distance sensing include for firefighters trying to find people in burning buildings, as well as for medical imaging and in autonomous vehicles.